Welcome to Math 1314. This is section 4.2 on exponential functions. The first question is, well, what does one of these exponential functions actually look like? Well, it looks like f of x equals a b raised to the variable x or y or t. The important point is the variable is the exponent, and the item on the bottom is usually a fixed number, which is called the base. So some examples. The first couple of examples here, we have f of x is 2 to the x, or 5 to the x, or 10 to the x. In the first case, b is 2, b is 5, or b is 10. And all of these b's are numbers that are bigger than 1. And that's important. We're going to see that in a few moments. And in these other two examples, I have 1/3 to the x, or 4/5 to the x. And this is if b is 1/3 or b is 4/5. And in these two examples, the b is a number that's a fraction, and that fraction is between 0 and 1. Well, we're talking about all these different b's. Which b's can we actually have? Well, there's only two cases. The b is bigger than 1, or the b is between 0 and 1. Now notice this does not include 0, does not include 1, and b is never negative. Again, the only b's that can ever be there are numbers bigger than 1, or numbers between 0 and 1, and not 0 or 1 themselves. Now often there's a confusion. What if you see f of x is minus 2 to the x? You might start thinking, well, didn't he say that b can't be negative? And yet right here it looks like it is. So the real case is this is minus 1 times 2 to the x. It's not this case where you'd have a negative number raised to the x. Now you might say, well, how do you know that? Well, if you look back to call order of operation in mathematics, some operations take precedence over others. In this case, being an exponent takes precedence over the negative in the front. That's why you know it's minus 1 times 2 to the x. Alright, so if the b, our number, is bigger than 1, the graph always has this basic shape. Well, what basic shape? Well, it crosses always at 0, 1. Why? Well, b raised to the 0 power, anything raised to the 0 power is 1, right? 2 to the 1, 5 to the 0, 2 to the 0, they're all just 1. Now the only case that's a bit strange is if you had 0 raised to the 0. But other than that, we don't have to worry. It always crosses here at 1. What happens? As we go to the right, b to the x grows quickly. And as I come toward the left, then we shrink down to this dotted line, which is called the horizontal asymptote, which is y equals 0. And it's going to have this basic shape anytime b is bigger than 1. The domain is all real numbers. doesn't have any breaks or jumps or strangeness. And the range, well, how low? Well, it never gets to 0. That's why it's a parenthesis. And it does grow upward forever. Now, what if we're in the other case? And that is that the b is a fraction between 0 and 1. Well, what happens is it just goes the other way. Still crosses at 0, 1, and still has this horizontal asymptote of y equals 0. This time it grows on the left and shrinks as we go to the right. Domain and range are exactly the same. Now let's look at the homework now that we know what the graphs look like. So in question 1 we have graph 5 to the x. Well, let's see. b is 5. It's bigger than 1. So I know it's going to have this particular basic shape, crossing at 0, 1. And then from my rough sketch here, I made the horizontal asymptote crossing at 0, 1, and it's at 225 because 5 squared is 25. Now that's easy to draw on paper. What do you do in Connect Math? Let's take a look. So I'm in Connect Math here. I'm looking at question 1 and they want me to graph 5 to the x. All right, let's open it up a little bigger here. All right, so I'm looking at this and looking, well, how do I do that? Well, let's see, I got an eraser to erase something I don't like, pencil if I want to draw it by hand. I've got a log function. I don't have one of those. I've got an exponential. That's my tool for exponential. Now, the best way is to plot 2 points. So let's do that. My first point I'm going to plot is, well, 0 and 1. Because I know 5 to the 0 is 1. So plot that point. And I'm going to pick one more, 2. And 5 squared is 25. Plot. All right, let's see where they're at. Did it plot them? Oh, it did. See how it plotted them? So now I'm going to pick my tool, and it says place the horizontal asymptote. Well, I know that it wasn't up there. It was here on the x-axis. Okay, plot the first point. Yep, that's my one. And now I come over here to my second dot. Click that. All right, that looks good. Let's see if it likes it. Oh, it did seem to like it. And then it's going to want to ask questions about domain and range. Let's do a few more of these just because I think it's important that you see this. I don't know why it keeps shrinking. All right, let's go here to question 2. 1/4 raised to the x. Well, let's see. I know it's going to, that b is between 0 and 1, so it's going to go the other way. I try my same strategy, which is to plot points. Well, I know one of them is, again, 0 and 1, because 1/4 to the 0 is 1. Let's see, I need another point. How about 1? So plug in 1. And 1/4 raised to the 1 is, well, 1/4. So I'm going to use this little fraction guy and type in 1/4. Plot the point. All right, let's see if it did that. Okay, yep, there they are. There's my 2 points. Get my tool. Okay, place the horizontal asymptote. Yes. First point here. Second point over there. Now the graph looks the right way and the right shape. So check the answer. And again, it likes it. A couple more. Let's see. Question 3. 3 halves to the x. All right, well, let's see. First off, how big is 3 halves? 3 halves is 1.5, so it's bigger than 1. So I should expect the graph to go this way. Plot some points. All right, let's do that. Raise it up a little bit. So I know one of them guaranteed is 0, 1. Plot the point. And let's see if I plot 1. 3 halves to the 1 is, I need a fraction, 3 halves. Plot the point. Let's see if it did it. Yeah, it's kind of tiny. Hopefully you can see it. So again, get my tool here. Place the asymptote. Yes. First point is, oh, I don't like that. I think I went too low. Did I? No, it looks okay. Here's my first point. Second point. That looks good. Let's see if it likes it. And it does. All right, try a few more here. Question 4. Oh, see, this one is a shifting. It's my basic shape of 2 to the x, but shifted up by 4. All right, so what do? I need to shift this guy. Let's see, where was it? Up by 4. All right, so grab the translation tool, and I go up by 4. So it used to cross at 1, and if I go up by 4, it should now cross at 5. Let's see if it likes it. And it does. So they're all basically like that. Let's go a little farther up to 7. Minus 5 to the x. Oh, there's my minus in the front. If you remember from graphing, it flips things over. All right, so let's see, how do I do that here? I need this tool, which is to reflect. All right, let's reflect. Oh, it did it automatically for me. That's it. It just reflected. It's not shifted left, right, up, down, just reflected. And check the answer, and it likes it. Okay. So let's go back and take a look at the homework now and see what we've got. So we left off there. Let's go here looking now domain and range, and let's go look at the homework here on question 2. All right, continuing here on question 2, let's see. We have on our pencil and paper method 1/2 to the x. So b is a half. It's between 0 and 1, so I know it goes that way. And again, like we showed you on the graph, I need the asymptote at 0, crossing at 0, 1, and I plot one more point, which I showed you before. You can plug in 1, which would be 1/2. You could plug in 2, which would be a half squared, or 1/4. So however you plot your point, and then use your tool to draw it. Domain is everything. Range is 0 on up. On question 3 here, we have 8/7 to the x. So b is 8/7. So the question you have to ask is, how big is this b? Is this b bigger than 1? Or is it a number between 0 and 1? Well, it's bigger than 1, so it's going to come this direction. Asymptote is the x-axis, crosses at 0, 1, and then you just need to pick one more point. And again, I would pick x to be 1, and then the output is 8/7, making it easy to calculate. No change on the domain and the range. So question 4 here. We have 2 to the x plus 2. Well, this is added on to the end, and on the end moves the graph up or down. So in this case, it moves it up by 2. All right, so if it crosses at 1, up by 2 makes it cross at 3. The important thing is the old asymptote was y equals 0. Now it's moved up by 2. Everything moves up, graph and the asymptote. So it was y equals 0. Now it's y equals 2. Domain doesn't change, but now it never gets to 2. That's why it looks like the following on the range. Domain has not changed. Horizontal asymptote we talked about was y equals 2. Now what about this one on question 5? 5 raised to the x plus 5. Now notice I'm adding 5 up with the x, not on the outside. If it were on the outside, that would be up by 5. But here, this is a left or right. Set it equal to 0, you get x equals minus 5, so it goes left by 5. So take your graph. So I take the important point, 0, 1, shift it to the left 5 units, and so now it's at minus 5, 1. And if I drag this thing to the left, notice the asymptote does not change. It's still y equals 0. Domain didn't change, range does not change, and the asymptote stays the same. Question 6. 3 to the x minus 4 minus 1. Alright, so the minus 1 on the end goes down by 1. The stuff that's here is a left or right. So x minus 4 is 0. So x is 4. So right by 4, down by 1. I always pick the easiest point, you see. So here it was at 0, 1. So where did I go again? Over 4. 1, 2, 3, 4, and down by 1. So that's where it would go. The asymptote is y equals 0, and if I go down by 1, it's now at minus 1. Domain doesn't change, but how high and how low does. And that's why it is minus 1 to infinity. The asymptote is y equals minus 1. Question 7, there's our minus in the front, and the minus in the front means minus 1 times 4 to the x, and so it's flipped over the x-axis. And that's why we use the tool to flip it over. And in this case, it looks like the following. Now, what changes? Asymptote does not change. It's still y equals 0. Domain, still the same. What changes is the range. It goes down forever and goes as high but never touches to 0. So minus infinity to 0. All right, question 8. We have this e business. Well, e is a number. It's about 2.7182, which means that e is bigger than 1. So it's going to have a basic shape like this one. But the x minus 6 means it's shifted left or right. Which one? set it equal to 0, and I get x is 6. So, right by 6. So take this point, shift it over 6 units to the right. The horizontal asymptote does not change, doesn't go up or down. So nothing changes in terms of domain, range, or asymptote. All right. Now, in question 9, we look at some banking applications. And for the first part of the banking application, we look at something which involves compounding periods. How often the interest is recalculated and added back in. The formula is the following. A is the amount of money we're going to have out at a future time. P is how much we invest now. R is the annual interest rate. And N is how often that the interest is calculated. So annually mean once a year, quarterly N is 4, monthly is 12, and daily is 365. We'll talk about continuous in just a moment. That's a different formula. If it's one of these fixed number of compounding periods, then it's this formula. So, what do they want me to do? It's going to stay in the bank for 9 years. So that's my T. T is 9. My interest rate is 3.7%. So divide that number by 100 makes R 0.037. So if I'm looking at annually, I'm filling in the numbers here. 19,000, 1 for the compounding period, 9 for the length of time, and here's my R. So that's pretty easy to calculate. You do that part first, add 1. Take this number, raise it to the 9th power as an exponent, and then multiply the final result by 19,000. All right, and then you need to round the number, so it looks like the following, 895. But if I round it to money decimals, that would be 0.90. Now, what changes if n is 4? All right, well, 4 is there, and 4 is here multiplied by the 9. Exponent is now 36. Now, the hard part here is the calculation. You want to keep it all in your calculator and not have it be rounded. So how do you do this? You first calculate this, 0.037 divided by 4 equals. Add 1 equals. Raise that number to the 36th power. Then multiply by 19,000, and once you round it to money, 26,467.25. For n equals 12, you just repeat this, and the only difference in the formula is the 12 there and the 12 there. And you simply grind through just like before. Now, and I didn't do the one for daily, but that would just be n is 365. When we talk about continuous compounding, we get a different formula. You can remember it. It's the name of a shampoo they used to make. I don't know if they still do, but the shampoo was called Pert. So it's P multiplied by E, our friend E. And if you look on your calculator, it's typically, there's a button on your calculator that has an ln, and e to the x is generally sitting above that key. So this is on your calculator. Other than that, I simply fill in my interest and the number of years, which is 9, multiply these two together, and then do this e raised to that power, and this is first. Multiply it by the 19,002nd, and this is the number. That's if the compounding to recalculate the interest was done all the time. So, continuous compounding has this formula. If it's a fixed number of compounding periods, it's the other formula. All right, and in question 10, they want you to do this for continuous compounding. T is 10 years. Principal is 14,000. Now, what's going to change? The interest rate. And so you simply grind through this for each of the different interest rates, and then round the result to 2 decimals for money. All right, in question 12, we have something involving half-life. When you have a chemical element that's radioactive, it has what's called a half-life. That means after a certain period of time, half of the substance goes away. It radiates outward. So in this case, strontium-90 has a half-life of 28.9 years. So what that means is the following. Let's say I had 100 grams of this substance. If I let it sit on a table and it sat there for 28.9 years, then I would be going down from 100 to 50 grams. If I go another 28.9 years, it would half the 50 again. So, my formula for this is the following. The amount you're going to have is how much you start with, and then 1/2 raised to the amount of time divided by the half-life. So in our case, we have 20 micrograms. All right, and they want it to be 86.7 years. Well, if you do this calculation of 86.7 divided by 28.9 is perfectly 3. That means that 3 cycles have gone by. All right, so let's see. You started with 20. You would half it to 10. Half it 10 again to 5. Half 5 again to 2.5. And if you do the calculation here, that's exactly what you see. If you use 202.3, turns out that's exactly 7 half-lives. 7 times the amount is halved. And so that would look like 0.156 micrograms. And if you did 289 years, that's exactly 10 half-lives for the item to go away. On a side note, that's how they do carbon-14 dating. of old items because they look how much carbon 14 is still present in the sample. That way they can know how old something is. Not exactly, but a reasonable number. All right, question 12 involves cooling. So, the idea is fairly simple. You put something in the oven and it's cooking. A cake, a turkey, whatever you have in the oven. And if you let it sit there for a while, the temperature of that item is going to be what's in the oven. If you take the item out of the oven, put it on the counter, it's going to cool off. And if I let it sit there for many, many hours, it's going to come to room temperature. All right, so let's see. See if I got a graph here. So for example, it came out of the oven at 350 degrees. It's going to cool down. The room temperature is 76 degrees. So the temperature is going to cool down on your item until it eventually reaches close to room temperature. Now there's a formula for this. The temperature of your item at any time is the room temperature and then the difference between when it comes out minus the room temperature. And this is times e to the minus kt. K is an amount of a cooling constant. This is e to a negative number to make it go down over time. And so in this case, the room temperature was 76, came out of the oven at 350. The difference between those two is 274. And they gave me the cooling constant was 0.046. Let's see. See right there. K is measured in that number. All right, so there's my function that's going to give me the temperature at any time t. And this is t in minutes. All right, and so they wanted it at 15 minutes. So put in 15, grind through this calculation, and we're down to 213 degrees. After 30 minutes, put in 30, calculate again. We're down to 145 degrees. And that's not cool enough. Why? Let's see. Our question was, it needs to be under 100 degrees Fahrenheit for her to put the frosting on the top. If it's too hot, the frosting will melt and run off the side. So, 30 minutes was not enough. I wonder how much time we would need. I don't know, we could calculate it at 45 minutes or 60 minutes and find out. I'll leave that to you. Well, that concludes this section 4.2 on exponential functions.